So let's start. Who was at the Red Hat keynote, or Summit keynote this morning? Yeah, Kyle, okay, okay. So who played the game? Ah, good. So you need to know that every time you touch a balloon, this was sending an event to a WebSocket managed by Vert.X. This then was translating this WebSocket frame to a Vert.X message, sending that to some other Vert.X application. And this Vert.X application was then calling one of the microservices that we had, so achievements, scores, and so on. And at some point, we get message that was going through the other direction, so from achievement and so on to your mobile, to your device. This was all powered by Vert.X. So in this talk, I'm going to detail a bit what Vert.X is and how you can make your microservice architectures much more reliable and scalable with Vert.X. So my name is Clement Escoffier. I'm French, as you can hear. So I have a strange accent. And I'm Vert.X core developer. So I'm developing Vert.X. And I'm working for Red Hat. So Vert.X in 10 slides. Vert.X can be defined as a toolkit to build distributed and reactive applications on top of the JVM using an asynchronous non-blocking development model. That's a lot of weird words in one sentence. So let's have a look to all these words. First, it's a toolkit. It's not a framework. It's not an application server. It's not a container. It's just a toolkit. So actually, what Vert.X is, it's just a plain boring jar file. Just a jar file, nothing else. Providing an API, and all the components that Vert.X provide are actually just jar files. So you can use them, it's just jar file, you put them in your class path, and here you go. You can use the API. So when you build a Vert.X applications, you will have your applications here. That is a jar file too. Then you have Vert.X and its dependencies, and that's all, just jar file. OK, so jar file, but we not necessarily use jar. We can use war, we can use OSGI bundle. Well, you can use Vert.X inside a war, inside Tomcat, inside Wildfire, inside EAP, inside Spring Boot. No problem. It's just an API, just a toolkit. It's really not a container. You can use a FATJAR, you can use a class path, you can use OSGI to manage this. You can even use GBoss module if you want. No problem for us. So these slides here, these slides are actually Vert.X application. It's a distributed Vert.X application, and you will see the other application I'm going to start will interact with this application. It's executed on OpenShift. So here, up here, it's this one here, one pod. Well, I'm the only viewer, so I don't really need scalability for that. We'll see scalability later in this talk. And it was packaged as a FATJAR with all the dependencies. So the first one is Vert.X core, then Vert.X web. Vert.X web is a component to build modern web applications. So this is HTML5 slides. And modern web applications, it's a web app where you have more JavaScript code on the browser than on the server. And believe me, in this slide here, you have much more CSS than any Java code that I will write, which is bad because I don't know anything to CSS. But, well, you might see some issue on some slide, by the way. Vert.X is made to build distributed application, and one of the core things in distribution is clustering. In this talk, I'm going to use Vert.X Hazelcast. It's one implementation of the Vert.X Cluster Manager. We have others. We have one based on Zookeeper, one based on Groups, one based on Apache Ignite. So it's up to you to choose the one you want to use. Actually, one doesn't fit all use case, so it's actually your use case that will dictate which one you want to use. And there is another component that is very important here. It's the Vert.X Service Discovery Bridge for Kubernetes. So OpenShift is running Kubernetes. And Kubernetes is an orchestration engine for a Docker container. It's really, really powerful. It has the concept of services. And actually, it will make discovering those other services that your application is calling very, very easy. However, this API is not a VertX API. So what we have is a VertX Service Discovery API, and this bridge will just consume the Kubernetes services to find them. We will see that in a moment, so don't worry. So VertX is made to build distributed applications, but we all love distributed applications. And in the 60s, people decided to build distributed systems because they were limited to one machine. So the CPU and memory and disk were too limited, so they decided to put more machines and to put wire in between these machines. That's great, but they forgot a couple of things. These wires here are a bit complicated. So we have developed many, many technologies to build that, to try to create distributed systems, and there is technology we all love. Technologies we all love, like DNS. So DNS is kind of my favorite technology since 3 weeks, as we just don't stop debugging DNS issues. Corba. Corba. Who liked Corba? Who did Corba first? Yeah, OK. 2? Only 2? OK, who did SOAP? Web services? So we are in the XML generation. OK. So there is many, many technologies like that well, let us kind of weird taste. It doesn't really work. It's slow. It failed. And actually, one thing about distributed systems is that it was defined by Leslie Lamport in the 80s with this sentence. A distributed system is something that is going to fail. I will add something. It's going to fail in production. On your machine, no problem. Everything will be fine. Latency is close to 0 and so on. But in production, when you are in real environment, when you have kind of a load, like this morning, when we got, I can't remember, 800 players at the same time, so we ramp up from 2 to 800 in a couple of seconds. That gives some loads. Well, you need to handle that. And you may fail, and actually, you are going to fail. A distributed application, you need to be prepared to fail. VertX is made to build reactive systems. I will use systems, not programming. I will come to that in a second. A reactive system has been defined in this manifesto here. And this manifesto was initially written by the people from TypeSafe, from Akka. But there are many, many people that have signed the manifesto and believe that this is a good way to deliver applications. It's not the only way. It's a good way. Reactive systems need to be responsive. That means when you popped a balloon this morning, you get the updates almost immediately. Your leaderboard was updating, your scoreboard was updating, your score was updating, so it was responsive. From 2 players to almost, well, this morning, so we were at 800, it has to be responsive. So it needs to respond in an acceptable time. I let you define acceptable, it really depends on your application. It needs to be elastic. Well, if you want to scale, either you buy a very, very, very big machine that's pretty expensive, or you decide to adjust the number of nodes you have according to the loads you are going to have. It's resilient. Reactive is mostly made to build distributed system, and distributed system fail. So you need to be prepared to handle those failures. If we stop here, well, this guy, I've written a manifesto, so as all manifestos, it starts by modern applications face requirements that was unexpected, blah, 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 blah. All manifestos start with that. And if we stop here, so that's the end of the first page, we say, OK, this guy just wants an application that works. An application that responds, that handles the load, and that manages failures. OK, they just want something that works. OK, cool. But they've added this one here. They said to work, this application needs to use async message passing. So that means we are not going to call something and wait for a response. We are going to send a message. If we wait on a response, then we will wait to get this response, but we don't know when it will arrive. We don't know even if it will arrive. That is the kind of failure that you can have. So why reactive is a kind of a big thing right now is, well, there is no free lunch anymore. Before, we had the Moore's law, and the Moore's law say, well, don't worry about your code. It's going to be fast. You don't care. It's going to be fast, and, well, no problem. And then we had the cloud and say, OK, well, we hit a limit, but don't worry, you can have thousands of nodes, so it's going to be fast, so don't worry. Well, scaling an applications like that doesn't work. Your applications are generally stateful, so yeah, start to be weird. OK. And the Moore's law stops working because, well, CPU vendors just fail. They fail to make CPU even faster and more efficient and so on. So what they did is pretty simple. They say, OK, one core cannot be faster than what we have. But no problem. We're going to have more than one core on the chip. And here we come with multi-core processors. OK, well, but multi-core processors, that's something that is a bit weird. When you have one core, basically you are executing one thing at a time. A single thing, a single instruction at a time. When you have multi-core, it's not the case anymore. You can execute, if you have four cores, four instructions at the same time. So to really benefit of this, you need to design your system, you design your application to allow parallel and concurrent execution. And this is something that is hard. We were doing that with MPI in the 70s, 80s, 90s. Well, so did someone use MPI before? No? MPI is a language to build concurrent programming. Have a look. It's kind of, whoa. It's not that simple. It's a bit spicy, let's say. So if you want to benefit from this multi-cores, you have to design and to use a development model that allows that. And reactive systems actually is one solution to this issue. VertX is polyglot. So your VertX application runs on top of a JVM. This morning, it was a JVM inside our container. This morning, the application was developed in Java, but also in Groovy, in the same application. The same application was using two languages. We could have used Ruby, JavaScript, and Ceylon in the same application. We don't care. All the VertX API are generated for all these languages. And even more, those ones are the official language we support. There is also a Python, Scala, Kotlin, TypeScript, and many more that are developed by the community where you can just use them, and all the API will be available for you. Something very important, it runs on top of the JVM, so it's not native. So for example, in Ruby, it's gRuby. So gRuby is really good. It's almost like Ruby. Well, I'm not someone that developed a lot in Ruby, so for someone that is really in the Ruby world, it is different. But from my perspective, it's not that bad. But for JavaScript, it's not Node, it's Nashorn. And this is a big difference. Nashorn is way behind Node today. So you need to be aware of that. If you select JavaScript, be prepared, because it won't be ECMAScript 6. It won't be, well, it will be pure JavaScript. Well, OK, let's now speak a bit about microservices. Microservices, I would say just rebranding distributed systems. Cool, so we are providing a new way to build distributed system where we are unable to build since the 60s. That sounds like a really great idea. And actually, we are going to mix technologies. We want loose coupling, and we want something fast and so on. Yes, everything is going to be fine. You saw that this morning. We were absolutely not stressed at all. So Martin Fowler has written this definition, so you don't have to read it all. The important part is that microservices are an architecture style. It's a style. I won't define architecture style. Previously, in a previous life, I was an academic, so there is an academic definition of what an architecture style is. It doesn't mean anything. So actually, what is important is that your system is going to be a set of small services. A set of federated services. That would have been actually the right name of microservices, federated services, because the value comes from the federation. Every service individually, no value. Actually, no value. But the federation of all those services, that has the value. All the services are going to communicate using a lightweight mechanism. It can be HTTP, but not only HTTP. It can be many things. And something that is very important is that all those services are going to evolve at their own pace. So it can be, well, a release for one, then a rollback for another one. All services will evolve at its own pace. And that's pretty cool. Because you don't have to think anymore. Well, a bit on the interface. Because if someone changes the interface, you probably need to propagate this change somewhere else. But for everything else, it evolves. So if one of your services has a bug, really a critical bug, you can push that immediately. And you saw that this morning. This is an important part that a lot of people forget to read. There is a bare minimum of centralized management. A bare minimum doesn't mean zero. There is no magic. There is no free lunch. If you want something that works, there is some management somewhere. OK, so let's go a little bit deeper on this. So microservices are, in 99.99% of the case, a distributed system. So you have to handle it. You have to think about that first. Its lightweight interaction does not mean it's not only REST, it's not only HTTP, it can be messaging, it can be streams, it can be RPC, probably async RPC, it can be everything we were doing before, because REST and HTTP, if you take all the interaction style, it's just one. There is many, many other ones. Pipe and filters, streamings, shared data, and so on. All those interaction styles are valid for microservices. These services are, as I said, developed individually, released individually, deployed individually, tested individually, using different pipelines. It should be automated. Because, well, how to say that? Executing a script on a production machine on a daily basis, that's a bit dangerous. So what we do is that we have some scripts that will be executed by an orchestration engine, generate Jenkins, your CI, or whatever, and it will do that for you. It provides substitutability in the least of substitutability sense. That means that if one of your services is not great, because, well, you make the wrong choice. It happens to everyone. You try this framework, it looks great, but, well, it's not that good, actually, so you want to change it. If you implement the same service, so the same interface, with another system, you can remove the first one and put the second one. What you saw on stage this morning with this blue-green is exactly this. We fixed something. Push it through the pipeline, and then it switches. Oh, it switched just because the services were the same. Well, with less bug, hopefully, but it's the same. So it's the same interface, so you can change. Microservices, with all those patterns, let you improve your agility. Not in the agile computing and so on, but really agility of the composition of your services. And so you can replace microservices. You can decide who is developing which microservices. They evolve at their own pace, so you are really, really more agile. So microservices are just about improving the time to production, not time to market. That's not true, time to production. But, well, the distributed system is low-scoped, so it's going to fail at some point. So there is no free lunch. It's not because you are using microservices that your application is going to be great tomorrow. Actually, it's even going to be more complicated than the same system if you developed it in a monolithic way. More complicated because, well, first it's going to be distributed, so there is more reason to fail. The communication can fail, but also every microservices can fail independently. Well, we will try to make that failure independent and not cascading, but we never know. Failure means fail stop, but also Byzantine fault. So you know those kind of services that you don't really understand why it's answering like that sometimes and why it's answering something else some other times? Well, those ones are hard. How to discover all your microservices? That's something important too. How do you know which one you are going to call? How do you discover this? how do you discover this in a way that it works on your machine, but it also works well in production? How to improve reliability, how to be sure that all your microservices are always ready to kick. So all this stuff, you need to handle them. And you need to keep that on track. So monitoring, health tracing, distributed tracing, and so on, and so on, and so on. So this is not only the responsibility of your ops. This is the responsibility of the dev, too, to think on the first line of code how they are going to monitor their system, how they are going to know when it's still alive, and how to know what's going on. So if you manage microservices, if we represent it like that, a microservices is far from being a single REST endpoint somewhere that you run. It needs discovery, it needs availability support, it needs delivery, deployment, it needs reliability, and then you have a second circle where we will have logging, of course, API management, how do you scale, how do you do load balancing, all the security concern, authentication, how do you get fault tolerance, or you get monitoring, and so on, and so on, and so on. So that's really, really complicated if you don't think that before you start implementing your microservice system. VertX and microservices, because, well, I didn't really mention VertX in this section yet. So VertX won't let you implement microservices. No, it won't let you implement, it will let you implement reactive microservice. And that's a big difference, because the microservice that you are going to develop with VertX will be fast, lightning fast. It will handle a large number of FN connections, and you saw that this morning. So it was working perfectly where we were 2 to 800 users in a couple of seconds. It is going to be elastic. We could have started new instances of the game bus this morning. I didn't. I was monitoring that, but I didn't. Everything was fine. And it has a built-in round robin, so you don't have to handle that. Resilient, failures, and you will see that in the development model, is a first-class citizen, really. So you can say, well, but this is going to be hard because, well, you know, in Java, we are using exceptions. Exceptions? What a funky name, exceptions. I handle exception every day, so they are not so exceptional anymore. Some are expected, all right. Some are less expected. And those ones, they are tricky to handle. So here you will have failures, and you will get results, and results of an operation can be a failure, so you will have to check yourself. New frameworks like and language like Node have failures of first-class citizen, like VertX have. If you look at Go, who did Go? Who did some Go development? No one? Oh, one? OK. In Go, every time you execute some operation, you need to check that the result was not nil. It's how they pass failures. It's how they detect failures. So yes, there is more code to write. Writing more code is not necessarily bad. If writing more code will reduce your productivity, we will all develop in Perl today. And we don't. So imagine this. To work, VertX is going to use an asynchronous message pacing, and we will see that right now. On the left side, you have traditional, let's say, application server model, and on the right side, you have non-blocking development. On a traditional model, you will have your connection, and this is going to be one thread, and this thread is going to handle your connection. So if the first thing you do is calling something in a database, no problem, you do that, but then you are waiting. OK, back. For 3 seconds, nothing happened. My thread is blocked. So if you want to take 800 users at the same time, like this morning, you will need 800 threads. Whoa, 800 threads? If I generate a thread dump, this is going to be huge. And I don't want to look at a thread dump of 800 threads, really. In a non-blocking, asynchronous non-blocking development model, I will be here. He will say, OK, I want to do that with a database. It will release immediately the threads. And it will be called when this comes back. So it passes callback, and this callback is going to be called when the operation is completed. But the threads can do B, can do C, cannot get some free time, can go partying, can manage something else. And when we come back, A can continue his execution. Something important may or may not happen. asynchronous operation may never be completed. That's part of the model. And actually, in distributed systems, that's normal, because we have some many issues, and we never know when it will be done or not. So what VertX will provide to build your microservices is TCP with UDP, HTTP 1 and 2 server and client, non-blocking DNS client, event bus for the messaging, distributed data structures, load balancing, failover, service discovery, failure management, circuit breakers, shell, metrics, deployment support, and so on. So you have absolutely everything to build reactive microservices. Let's start with some REST examples. So that will probably be your first code you will write in VertX if you start VertX. You get a VertX instance. We will show that. Instead of doing that on the slide, let's do that live. Here, this is going to be the application I'm going to run. So I have a main class. Oh, yeah, I forgot that. Oops. So you have your main class here with your main endpoint. So to start a VertX app, you are going to use a main. Woohoo! So you don't need to kick off a container, an app server, or whatever. Just a main. So if you want to run that locally, it's right-click, run. That's all. You want to debug that, right-click, debug. You want to provide that, right-click, profile. That's all. Then you create a VertX instance using vertx.vertx, and then you create your HTTP server. You will pass two handlers here. The first handler will be called every time you get a request. So every time you get a request, we are going to answer with DevNation. I will write the time, and I will write the thread name. You will see that this in a second. The second, so this will be asynchronous. We don't know when the request will come, so this will just catch it, execute this. The listen part is when we start the HTTP server. This is an asynchronous operation, because starting an HTTP server takes a lot of time. Seriously, there is many things happening in the operating system level to find the right socket, to do I have the right to do that, and so on. So here we say, OK, I'm starting to listen on the port 8080. And when it's done, this handler here, so this part, is going to be called. This part here, this result, is what we call an async result. It's a data structure that is provided by VertX, and they will tell you if the operation has been successful or not, because starting an HTTP server may fail. For example, you have another one on the same port. That happens to me every day. And if it's successful, then you get the result with result.result. So yeah, OK, it can be a bit, lots of code to handle that, but you need to handle failures the right way. So this has been deployed. So I have a Docker file here. So I've deployed it on OpenShift. As we have only 1 hour, everything is already deployed, because if not, then it will take 15 minutes just to deploy. Let's call it. So if you want to see which one it is, it's probably that one. That one. We have one pod right now. Everything fine. It's running. Cool. So let's call it. There we go. And every time I call it, well, obviously, I need to be a little less fast, because my operating system tried to, I know what invoke means. So every time it prints the dates and the thread. Well, come on. Every time I'm called by the same thread. How come? And what is this name? Event loop. But what? Event loops? What does that mean? Oops. Actually, VertX is based on an event loop system. So event loops are not new. Event loops exist since the 50s. So even before, or lots of things. And an event loop can be summarized with this. You have a set of events. You have a queue of events. Cool. Then you have an event provider that will push events there. So for example, a request, HTTP request is coming. Then you put this. This is an event, so you pass it there. And the event loop will say, OK, it's a thread that will do get next event, find the right handler, call it. Get next event, find the right handler, call it. And never stop. Now, this is great, but it works only if your handlers are non-blocking. Because if your handlers start to do heavy computation, I/O or whatever, then there is something that doesn't work. Your events will queue up until you run out of memory. and you will kill the whole system. So the golden rule or the golden rules of Vert.X is never block the event loop. OK, so that was a server. So let's call it A. But when we do microservices, we are calling services. So we may have another service that we call this service. To do that, if we stay in the HTTP world, we provide an HTTP client. This HTTP client here, so you just create it like that. Then you pass a set of options, like the default port, host, and then you do get now, the pass, and you get a response. So the first handler you pass is getting the response. When you get the response, this will be executed. The response doesn't mean that you have the body, because we have chunk requests and so on. The response means, OK, I've established a connection. I got the first thing, so I got the status message and the headers. That's all. If you want the body, you need to pass a second handler, which is a body handler. And once the body has been collected, then you are ready to use it. So it's nested handler. So obviously, you can say, well, it's nested handler. The development model is going to be a big mess pretty quickly if you do that. And that's right. So we provide future support with future composition. We provide Java RX support. We provide reactive stream support. So all our API are RX compliant and so on. So you don't have to manage your handler like that. This is just an example that you understand how it should work, how it works. Actually, the most of the VertX core code just use handlers. One thing here is that how do we discover this? Host and ports. Because, well, if you are on your machines, it's probably going to be localhost 8081. But if you are in production, that's not going to be localhost. That's going to be something very different. You don't know the port, you don't know the host. It may even change. So you need some discovery here. So Vert.X comes with its own discovery mechanism, where it's very simple. It has kind of a central management that is actually a distributed map. You have service providers that can publish, withdraw services, and then you have consumers that will just look up, listen for change, being notified, and so on. But, well, I'm on OpenShift here, and when I started my system, I did, well, OK, route this port on this. So I kind of already have made this publication. Good news, we have a bridge system that lets you import and export services from almost any discovery technologies. In Kubernetes, it will read the services from Kubernetes and import them. So you don't have to publish them, just consume them. Let's have a look. I want to discover the service that is named with its name is VertX HTTP server. So I use this file here. I know that it's going to be an HTTP endpoint. Well, if you don't know the type of services, you cannot invoke it. So you know that. You do get client. You pass the discovery service. And you pass the name. So this is a filter. You can have more than one attribute. You can even pass a functions if you want a complex computation. And when it's done, you get it. What you get directly an HTTP client with the right configuration, ready to be used. Nothing else. And then you do the get now, and that's all. Let's do that. So this code is exactly this one here. I have created here the service discovery. Then I say, OK, I want to use a Kubernetes service importer. And that's all. Then you configure it with the name of your projects. Actually, depending on how you work, how you run, you don't even need that, because it's written in this environment variable. And the Kubernetes bridge is going to pick that one automatically. So we have a set of environment variables that we check. And then, well, when I get a request on slash, I just say, OK, give me the client, and I call it asynchronously. So when I get a slash, then I get the client. Then when I get the client, I do the call, and then and when I get the response, I register the body handler, and when I get the body, I reply to the request. None of these calls are blocking. But all this is going to be executed in the single same thread. Let's execute that. So this is overview here. OK, this is this one here. So if I go there, oops, shit. do invoke. Here we go. What it did is that it called the first server I have, so that was A here, so the one we deployed. Then I did what I did so with the HTTP client here. It got the body of this request, and it prepared hello, so now it's hello DevNation. Very simple. All asynchronous. Nothing is blocked. The same thread is going to handle a lot of loads. But actually, VertX is smart because it won't start one event loop. It will start as many event loops as you have CPU cores. So you can imagine to scale that pretty well. But once your object has been touched by one event loop, it's guaranteed that you will always be called by the same event loop. That means that you don't need synchronization, you don't need volatile, you don't need lock, you don't need to debug a deadlock in production at 2 EM. I know you loved that. I actually did, so. OK, that's cool, but HTTP is right, but sometimes it's not really asynchronous. How does that work when I am calling something that is synchronous? VertX provides you an execute blocking operation that has two handlers. The first one is executed in a background thread, and then the second one is when this background thread has been completed, will be back in the event loop. So you are in the event loop. You are not allowed to block. This is a golden rule. Then you say, OK, no problem. Here is the code I want to execute on a background thread. You can tune it. You can do whatever. You can, that's a thread pool. And it does the blocking operations, like discussing with the database. And when it's done, when you have the result, you complete the feature here with the result. It gets the result here, and you are back on the event loop. So you are not blocking the event loop. So you can discuss with almost anything. Recently, in VertX 3.3 that was released on Monday, we even go further. We have integration with Apache Camel, so you can interact with everything. Well, Camel is great for this. Oh, OK, so that was kind of request reply. That works for HTTP. It also works for TCP. Let's now do some stuff with the messaging. The event bus is an event bus. It's a nervous system of VertX. It allows any other VertX application to discuss with this. Any means regardless their implementation language. I told you this morning we had Groovy and we have Java. They were communicating using the event bus. Regardless their location, they can be on the same node. They can be on the same cluster. We don't care. And this is important. Whether or not they run on VertX. VertX application can, of course, discuss with the other VertX application. But unfortunately, right now, there is some other stuff than VertX. And this other stuff, like Node, like Java EE, like Wildfire Swarm, like .NET, like Go, like Rust, all this stuff, we want them to interact with the VertX app. So why not? So we provide clients and bridges that let you interact with the event bus. We are going to see that with an example with Node. The event bus has two concepts. We don't like very complicated things in VertX, so we put only two concepts there. First one is addresses. Addresses are opaque string. No hierarchy, nothing. If you want to use only space and tab in your address, you are. But that's not probably very readable, but you can. And the second concept is handler. Good news, we already saw handlers. So handlers are just Lambda that will get the message and will handle it. So how does that work? The event bus provides three modes of delivery. The first one is point-to-point. You have a sender that sends a message on a specific address. The consumer here is listening to this address, get it, and so his handler is called and can do whatever he wants with the message. Obviously, if we do point-to-point, we are also being able to do publish-subscribe. So instead of send, here you use eventbus.send, here you use eventbus.publish. We have a third one, which is interesting. The sender can say, OK, I send you this message on this address, but I'm expecting a reply. The consumer here receives the message and can say, OK, I want to reply to you, and take message.reply, and it will go back to the sender automatically. You don't have to configure anything. With this, if the message are named, I don't know, as a field like object name and something called method name, and then parameters 1, 2, 3, That was the message. The consumer gets that, do something, and reply with a result. Come on, this is RPC. This is an asynchronous implementation of RPC. You can do that with this. RPC is not bad. It's not because it's not hype anymore that you won't use it. Actually, RPC is very, very reliable and very well used. So the event bus will let any VertX applications that are part of the cluster to discuss using events, because the event bus is clustered. But thanks to clients, we can have native binaries application communicating with the event bus thanks to a TCP connection. So every language that is able to open a TCP socket and read JSON can interact with the event bus. That includes COBOL. COBOL has TCP, and COBOL is able to read and write JSON. Well, probably using strings, but it's already a good start. If you have something a bit more, let's say, JavaScript-ish, like Node or the browser, then there is another bridge that will use a WebSocket. Actually, not a WebSocket. It will degrade smoothly to iframes. I will come to that later, to interact with the event bus. So let's have a look. That's not normal. OK, so what I have here, I have started an application that is a VertX app. Let's have a look at its code. It's that one here. That just send, get the event bus here, and published on this topic here, on this address here, sorry, this JSON object. So if you're in Java, we are using this API to avoid creating too much objects and so on. If you are in JavaScript, using VertX in JavaScript, then it's just a JavaScript object. If you are in Groovy, then it's maps and so on. So depending on the language, how you create JSON objects is a bit different. It's really native. So, and this is sending, so this runs in its own pod on OpenShift, on own node. It's published message. The slide application got them and sent them to my slides. Look, my slides are getting these events. And one every 2 seconds, 3 seconds. Well. OK, let's go further. I also have a node application that is not started yet. Let's start it. I start the application. Whoops, the pod is now ready. OK. I check the log. It's always good to check the logs because with Node, sometimes I have surprise. Yeah, so it's connected. And now if I go back here, it's your French time, bonjour, from Node. Here. And every 3 or 2 seconds, it's going to write bonjour from Node. That's all. We have a Node application. We have a VertX application sending events to my slides. It's the same thing that was happening this morning, except with that we didn't use Node to push events. So how does that work? Actually, here, in this demo, I'm going to use this Sergius bridge. So Sergius is a JavaScript library that doesn't use LeftPad, and that is more than 6 years old, or 6 months old. So imagine for JavaScript, it's whoa, like retirement time. But what it does is that it has a handshake with the entity that want to connect. It will start to check if WebSockets are supported, and then it will degrade to SSE, long polling, Ajax, and if you are using Internet Explorer 6, it's going to use an iframe. But you should not use Internet Explorer 6. My Node publisher got an NPM, so we have an NPM, VertX NPM on the NPM, to connect to this bridge, and then he has the same API, publish, send and reply. And the browser, same thing, it gets Bower, so it gets a JavaScript library that is available from Bower, NPM, or almost everything you can imagine in the JavaScript world, and you can just consume that. Something important here is that it's an event, but it's not the only event messaging that exists. We have GMS, we have Stomp, we have MQP, we have, and so on. We provide bridges and clients for all these ones. For Camel, let's speak a bit about Camel. Camel is really cool because it's a mediation framework that will let well, that manage interaction with almost everything. They have more than 100 components to connect everything, payments, and so on. With the Camel bridge, you configure your routes, you configure your bridge, and you say, OK, when I send an event on this address, it's collected by this bridge. This bridge invokes the Camel route. It goes somewhere. Then you get a reply in the exchange. And we reply. We send another event on another address. So you can interact with mostly anything in an asynchronous way, because the event bus is fully asynchronous. So thanks to this Camel bridge, you can connect to almost everything. So you can have your VertX app, reactive, and so on, connect with your existing legacy system. OK, well, we are humans. We make bugs, but it's and it's a distributed system, so don't be fooled. Be prepared to fail. There is a couple of ways to handle failures in VertX. The first one is to use timeout. When I do a send and reply, I can say, OK, I'm expecting a reply in 1 second. That's something we can do. However, just a bit of theory. So before I was an academic, so it's my theory time. Timeout doesn't mean that the operation has not been executed. Timeout means that we are invoking something, and something went wrong either on the way to the operation is executed, inside the operation that is executed, or on its way back. It doesn't mean that the operation has not been executed. And we know that. It has been proven since 1985. When you do a distributed system, timeout doesn't mean that it has failed. You need to be aware of this. That's kind of, ooh, how do you manage that? Actually, we'll live with this pretty well. Here, what you will do is that, OK, if I don't get it, I have this reply here, so I didn't get an answer. And if not, then you got a mail. So you get the results. Let's do that. So here I have another consumer that is very, very picky, because alternatively, it will, well, it has just a random boolean, and if it's true, it will just fail. So sometimes it will be there. Oops. Nope. So it's not started. Let's start it. Why it's not started? Where it is. I don't know which one it is, so, oh yeah, it's not deployed. So let's do the same thing with HTTP right now. It will be the same demo anyway. With HTTP, you can use timeout, and then you have an exception handler. So it's not really the same thing. On HTTP, you can register an exception handler that gets the exception, and that means that something bad happened. Here, you have 2 exception handlers, and that's pretty important. The first one, which is this one here, inverted. This one means that you was not able to establish a connection with the server, like, well, the server is down or something like that, or it doesn't answer in 3 seconds. This one is on the response subject. You got the connection. The connection works. You are going to read the body, but while you are reading the body, something bad happened, like body cut and so on. In that case, this exception handler is called. 2 different ways, because it's 2 different types of failures. So let's do that. Hopefully this one is deployed. Yeah, this one is deployed. Oops, OK. So let's stop A. So that is that one. Yes. So A is going to be stopped. So so I'm establishing it. I don't have any answer in 3 seconds, so I got this timeout. If I restart it, 2? No, I just wanted 1. OK, we can have 2. We don't care. 2 will be 2. Let's try. Which one do we have? Oh, no, it works. So it's back. We may even have 2 now, but so. We don't care because Kubernetes is going to do the load balancing for us. OK, so last reliability pattern, really popular in the microservices architectures is a circuit breaker. So circuit breaker, again, it's not new. It exists in the 60s and so on. Circuit breaker is very, very simple. It's an automata with 3 states. First one, When you start, it's closed. Everything fine. This circuit breaker will be there to monitor an interaction. So for example, an HTTP request and so on. And every time it has a failure, good news with VertX, it's very easy to detect if you have a failure or not. It will just keep the number of, it will keep track of the number of failure. And when you reach a threshold, you say, well, you are calling this server, but this server looks a bit shaky at the moment. So let's go to the open state. And in that case, don't even try to call this server, just fall back immediately. So that means that your server here that was shaky, maybe it was updating, maybe it was under load and so on. Here, you won't call it anymore. So he has time to relax. He has time to recover. He has time to be back on track. However, periodically, the circuit breaker is going to let the next connection to this server pass and check if it's a failure or not. If it's a failure, OK. It didn't reboot it. It didn't restart. It's still in vacation. OK, no problem. And if it's fine, then we go back to the closed state, and we are calling. We are going to call that again for the next connection. There is many implementation of circuit breaker. Netflix Estrix is the most common one. VertX provides its own. Why? Because it's asynchronous. The VertX circuit breaker is asynchronous, won't blocking. You can use Estrix, but you need to be careful because Estrix is going to use different thread pools and different thread models, so you have to use the right one. We have examples on how you use Estrix on VertX. So if you prefer Estrix, no problem. How does that work? I have a circuit breaker. I have configured it. And then I execute some code with a fallback. This will be my call. So I call this HTTP server. And if it fails, then I call the fallback. And that's all. That's all. It will do all what we say with a couple of lines of code like that. So everything fine. A is there. We may even have 2 A now. How many A do I have now? Let's stop it. It's going to 0. Oh, closed here means that the circuit breaker is still in the closed state. So every time I wait a couple of seconds until I detect the timeout, so it's probably 3 seconds here. And after a number of failures, we go in the open state. In the open state, obviously, I don't wait. The fallback is executed immediately. OK, now my server is coming back. Well, take a bit of time. Should be back now. So let's see. Back. What happened is that after a couple of milliseconds, it switched back to the half open state, and the next connection passed, and everything is fine. So now I'm back in the closed state, and everything is fine. So I could have updated my server. I could have updated my application. I have no downtime with that. I just manage the fallback correctly and the downtime correctly. So that's good because that lets you implement reliable application, distributed application. But we never know. You may become famous one day. And if you want to become famous, you need to prepare to become famous. So all we do is pass from 2 users to 800 users in a couple of seconds by using scalability pattern. VertX has a built-in load balancing. How does that work? That every time you send a message on the event bus, it won't call always the same consumer. It will just implement a non-strict round robin. So if you have many, many messages opening here, they will be dispatched among these 3 consumers. Let's have a look. I now have, how many consumers? I have 1. And if I send events to that one, I always got, oops, again, sorry. It's always handled by the same event bus consumer, which is named Butu-ut. Then I switch to 2 because, well, I want to be sure that I will handle the load, and I have a peak-off load that is coming. I know that, so I start 2. And now, load balancing, done. See, it's 1 and 1. So now I have 2 nodes that are going to handle the load. This morning, for 800, we use 3 nodes. for 800 users, 3 nodes. And actually, I was monitoring it. 2 would have been enough. OK, but that was on the event bus. How does that work with HTTP? So on Kubernetes or on OpenShift, first, it has a built-in load balancing on the Kubernetes side, so you can just scale this. Or you can just take your request or your WebSocket events and map them on the event bus. And this way, you can reach a high level of concurrent connection, really a high load, and you will scale almost unlimited. OK, I'm going to wrap up that. What I present here, it was mostly only VertX core here. VertX is much larger than this. We have Camel, I spoke about that. We have Mongo, we have GDBC, we have Stomps, we have reactive streams, we have web, we have metrics a lot. We have MQP 1.0 and 0.9. We have Docker support, GCA support if you are doing Java EE or Wildfire Swarm, and so on and so on and so on. So it's really large and it's bigger and bigger, actually, ecosystems. It's really an implementation of reactive systems, not only reactive programming. Let me discuss about that. Reactive programming is just a development model. Reactive systems are responsive, elastic, scalable, and asynchronous. Reactive programming will just give you a way to organize your code when you handle streams or asynchronous streams. It doesn't give you elasticity, responsiveness, and resilience. It just manages the asynchronous part. But the good news is that you can use reactive programming to implement reactive system. It's actually what VertX is doing. All the code I show you is reactive and use reactive programming. I could have used Rx Java. I could have used other reactive programming API. But based on this, it makes your system reactive, the whole system. It will be fast. It will handle the load. You can, and it will manage failure smoothly. OK, a couple of links to finish this. First one is VertX.io. Everything, all the documentation of our module, and the documentations are for all the official language. So you have the documentation for Groovy, JavaScript, and so on, and Java, of course. Introduction to VertX is a blog post series. There is 6 posts, actually. I need to write at least yet another 6 posts. It will let you. It explains how you start a Maven project, or you start VertX, or do you do the unit testing, integration testing, or you do GDBC, or you do Mongo, or you do REST API. If you're interested into that, that's the second link. The third link, it's a lab. It's a lab that is around 60 pages long, so it's a big lab. It will explain you everything around VertX and microservices. Discovery, how do you mix HTTP, event bus, and so on? How do you scale? How do you use circuit breaker? How do you use discovery, and so on? This is this one. The last one, VertX examples, just a repository with more than 400 examples in all language we support. So you have really, really a lot. So if you look for how do I do that, look at this. There is probably an example for this. Last things I want to show you. Oops. No, I won't show you that. No. Let me check. Did I provide it? Oh, no, I didn't provide it. So no, I won't show you the discovery page because, well, actually, it will be just there. That was a service we run in this demo here. VertX has discovered all of them thanks to Kubernetes and lets you build your cluster out of that. So using Kubernetes Hazelcast support and contact all the different nodes, either using HTTP or the event bus, using these services here. You could be something that is not Kubernetes. It will be the same thing, because it will discover the services using the right bridge, and that's all. So thank you. If you have any question, I'm here. So your turn. Yes? So difference between VertX and Akka. Both are pretty close to the agent model, actor model. Actually, one of the first reactive systems are agent model from the 60s, so reactive systems are not new either. Yes, there is a couple of differences. Akka is really a framework. It's not a toolkit. So you develop really for that. You cannot really embed it, and it's not easily. AK has really cool features, such as supervisions and reliable messaging. Our messaging right now is not reliable to be fast, because reliability comes with a huge cost. The AK supervision, so restarting a node, an actor, if it crashes, we do have exactly the same, but in addition, we provide you all the API to build your own supervision framework, because your application is unique. It's your applications. It won't be the same as the other one. You can try to use a framework that use exactly the same thing, that provide a framework really strict, that say, well, it should be developed like that. You will see pretty quickly that when you develop your application, sometimes you need to go beyond the limits. It's where interesting things happen. What happens if you go beyond the limits of a framework? It's something that we don't have in Vert.X because we are not a framework. You can build your own framework with your own rules on top of Vert.X. This is something you can't really easily do. You can't do it with AK. AK is only, I may be wrong, but I think it's only Scala and Java. We have much more things. And we have, thanks to our bridge, Go, Rust, any language using supporting TCP and JSON, being able to communicate with this, with the rest of the Vert.X applications. AK doesn't have this right now. Any other question? Then, in terms of programming model, it's pretty close. Huh? The threading model of AK is a bit different. That's all. OK, thank you very much.